gate across the mathematics of this. This is actually mathematically quite difficult. Now, again, if you have, it's an either or scenario here. If either the distance from the source to the slit is small, then you can see the incoming wave fronts will still be significantly curved, yeah, if that's close. Likewise, even if the source was off at infinity and we're considering the slit to be sources of secondary wavelets, well, these will also be significantly curved unless this distance goes off to infinity. So you need both the source to be a long way from the diffraction object, usually an aperture, and you need the detector to be a long way away so that you can use the far field plane wave approximation. So if you've got a distant source, you've got plane waves arriving, and even though the aperture itself is then causing, even from plane waves, some curvature, by the time you go to a really distant screen, you've again got effectively the plane wave approximation. Now, we're not going to be bothered with doing things in practice. Of course, in practice, this is slightly harder to arrange because you want to make the rays parallel. And in fact, what you usually do in real Fraunhofer diffraction is use some kind of lens here to make the rays parallel on before they hit the diffracting object, and then likewise you use some kind of lens here to bring them to a point even though they're parallel before the lens. And that's, I mentioned, we're not really studying geometric optics in this course. If you're doing Phil's course, you'll certainly know that's very straightforward optics, how to place a lens in order to achieve that. And again, I'll make some proper, actually I think that's such an important point, we'll actually start straight away with that. So we're going to be mostly studying, you'll probably be relieved to hear, the far field plane wave approximation, so I'll put that one first. So the far field, which is also called Fraunhofer diffraction, I think both these scientists were kind of famous in the early 19th century. A lot of these things were empirically been observed for light well before the Maxwell equations offered a coherent explanation for all these phenomena. So in this kind of diffraction, both, let's underline this, the distance from the source, it's called the source S, and to the diffracting object. And as I say, usually this is just going to be an aperture. In particular, today we're very rigorously going to do the Fraunhofer case of single slit diffraction. But you've got to have both that distance from the source to the object and the distance from the object to the screen. Or, in general, a detector. Usually, because we're going to be considering mainly light, we'll just say a screen, and somehow we can measure the number of photons on the screen. But of course, we may have electromagnetic waves of different frequencies, and we may have a more general type of detector. Well, both those distances must be large. And that's illustrated in figure 67 of the course handout. And of course it's not good enough in physics just to say large. Is this large compared with a nucleus, large compared with a banana, large compared with a, you know, a sort of Apollo space rocket, and so on. We'll come to what we mean by that in a couple of minutes. So Fraunhofer, you've got plane waves arriving at the slit, and you've moved your detector far enough away that you can also use the plane wave approximation at the detector. So if either again, let's emphasize this, if either the source object, because that causes the arriving waves to be still spherical, or the object detector distance are small, if either of those are small, In the diagram there, they're illustrated as both being small. The source is close and the detector's close. But if either of them are small, we get, and I say this is much more difficult to study mathematically. It's called near field or Fresnel diffraction. So these are just names, if you like, and that's how we label up what we're studying. So we've got these two types of diffraction. We've got the near field and the far field diffraction. So what do they actually look like for a single slit? Well, that's illustrated in figure 70 of the course handout. So this illustrates the transition from Fresnel to Fraunhofer diffraction. So in this case, we've got a plane wavefront arriving, and the waves arrive and then they're incident on a slit here. And this is supposed to be an opaque screen, so all the light from all this part of the wavefront just simply gets absorbed. That's all absorbed, that just disappears, but some light passes through. Now, the kind of interference work that we did last time, for example, we looked at the zeros in the Fraunhofer diffraction pattern, and we can see that the kind of thing that we looked at before, this sort of Loch Ness monster function, as called it, from a diffraction grating, we also get from a slit. We'll see why in the maths as we go along. And you get these little side lobes as well. That is specifically the far field approximation. Everything we did last week was interaction of plane waves. They were plane wave fronts. Everything that we did in our interference studies was in the far field. And the reason that I introduced near field diffraction into this course is that you don't get kidded into believing that's all that happens. It certainly isn't. If I put my detector at some distance P3, which is a long way away, so that I'm back in the plane wave approximation, then I can calculate this pattern using the techniques we used last week. However, you'll see if I put my detector really close, this is out here, this is the far field, this is the Fraunhofer pattern, the near field pattern is completely different. There are no zeros, and you'll see you get lots of small wiggly fringes, and this is the so-called Fresnel interference pattern of a slit, which you observe close to. Now, just to emphasise, there's no one distance where suddenly you switch off Fresnel and you switch on Fraunhofer. The wavefronts are getting gradually more and more parallel as they move away from the slit. And so there's a regime in between where the diffraction actually doesn't look particularly like either. So if you put your detector somewhere in between, then you get a sort of like neither one nor the other. It's starting to sort of become a little bit more like the distant interference pattern, but again, there's still no zeros in it. There are no nodes in this pattern at all, and you'll see it's got a longer kind of roughly exponential looking tail. Now, what you normally say is the cross, and this is a rule of thumb, this is not any absolute rule of physics at all. You would normally put your distance to your detector at what's called the Rayleigh distance, R, to ensure that you're looking at Fraunhofer diffraction. Like, say, for example, you're actually doing an X-ray diffraction experiment. You know the wavelength of the radiation and you want to find out how far apart all the atoms are in the solid. Well, obviously, you want a simple diffraction pattern to interpret, so you move your detector arm a long way away from your sample to make sure that that's the case. So what is this distance? And that's the next very simple equation. Remember, it's an approximate equation. So in optics, for a slit of width W, this is the case we're going to be concerned with almost all through this lecture. For a slit of width W, the transition occurs. This is the transition between near field and far field diffraction. The transition occurs and it's called at the Rayleigh distance, again obviously after the scientist who worked a lot on this. I should say too, in the next lecture we're coming up to something called the Rayleigh Criterion, which is totally unrelated to this. You know, he's a famous scientist, he did lots of work on optics. The Rayleigh Distance is where you go from your Fraunhofer to your Fresnel diffraction. And it's usually written as capital R, and it's given by a very easy equation. R is equal to W squared over lambda. I won't bother to do lambda. We've been using all the way through as the wavelength of the radiation, and this is illustrated in figure 70 of the course handout. So again, if you want to think in orders of magnitude, then a typical diffraction slit would be, let's say, of the order of a sub-millimetre, but then make it very easy on ourselves, about a millimetre. Then the wavelength of the light is about a micron. You know, we're just doing things very roughly here. Red light's 0.65 of a micron or so. Then you've got the 10 to the minus 6 divided by 10 to the minus 6. You'd have your Rayleigh distance of a metre. And indeed, that's precisely why when you do laboratory diffraction experiments and you send things through sort of 5 times 10 to the minus 4 metre or half millimetre slits, why you move your screen a metre away, because then you get something simple to interpret rather than this, as we'll see, very complex pattern close to the slit. So that's to emphasise the background, and we'll come back to the near field diffraction because Fraunhofer diffraction is the most important, because that's the one that's used. And you can see too that if you have diffracting, let's say you're doing X-ray diffraction now, well, your W you'd now interpret, if you like, as the separation between atoms and a solid. So you're talking about a few times 10 to the minus 10 of a metre. This is also 10 to the minus 10 of a metre, but this is squared. So you can see the Rayleigh distance is incredibly close. For X-rays, you don't need to move your detector a mile away, because W squared over lambda for X-ray, even though the lambda of X-rays is down to 10 to the minus 10, your diffracting slit, effective diffracting slits are also 10 to the minus 10. So almost any physical distance you put your detector, you're in the Fraunhofer regime, and it is the most important one. So that's the one we're going to analyse in detail. So Fraunhofer diffraction is easier to analyse because we can use, as we did all last week, the plane wave approximation. And that's why, of course, we've focused on it, because it's conceptually very clean to analyse with plane waves. And there's no doubt about it, the prototype problem, we can't analyse this one, we can't analyse any. So let's really knock this one on the head today. The prototype problem is single slit diffraction. In other words, we send a plane wave through a single slit, and this is, and we calculate the pattern in the Fraunhofer regime. And this is illustrated in figure 71 of the handout. So let's have a look at that. So, we're now specifically going to calculate exactly this problem, where a plane wave arrives on a slit. So let's change that to of width W I'm going to use, and the light rays spread out. There's interference, or if you prefer to call it diffraction of the waves, and we get this characteristic pattern. Well, how are we going to calculate that pattern exactly? And the answer is shown here. I'll come back to the phasor diagram way of representing it at the end. Let's just set the problem up. Now, you'll see here the slit is running from minus W halves to plus W halves, and we've chosen the origin here. We've continued, remember we're always going to use a plane wave that's going as e to the I kx minus omega t. So clearly we've got the wave direction in the x direction, and we've got the y-axis representing moving along the slit. Yeah. So in particular, you'll see straight away, if I plot the, if you like, the scattering power, again, I'm not going to be too, I've been slightly coy about absolute amplitudes all the way, we'll come back to that. But clearly, if I plot the amplitude as a function of y, going along the y-axis, I keep going along and I get absolutely nothing, yeah, because all of the wave is just absorbed here. This bit is just an absorbing bit. Then suddenly, at this point minus W halves, the scattering goes up to some finite value, depending on how bright the source is, basically. And then, as I keep going along to plus W halves, I get uniform illumination. I've got a great big plane wave. It illuminates this slit, forming a lot of second, and we're going to consider it as an infinite number of infinitesimally spaced sources, and then suddenly at plus W halves, as I'm going along the positive y direction here, the scattering goes back to 0 because all the wave front up here just gets absorbed by the screen. And hopefully from what you've been doing with Phil, you'll recognise immediately that what's called the aperture function, in other words the function that characterises the aperture, is a top hat function, centred on the origin in these coordinates and extending from minus W halves to plus W halves. So just to emphasise, you see this idea here, you'll see this refers here to a reference plane which is drawn exactly perpendicular to the line that connects the slit to the detector. Some point at infinity I've got my detector, and it's exactly the same thing. The maths is just the same. Remember, it's plane wave approximation. It's just like what we did for this 5-source interference pattern, yeah? We chose a reference plane that was exactly at right angles to this point at infinity, and then in that 5-source interference problem, well, we had to, of course, add up 5 waves. And if I chose this one to be the origin, I have to keep adding phi, 2 phi, subtract 2 phi, etc. Because these waves have travelled this little extra distance and these ones haven't. So all that I now do is, you imagine I keep filling in all these gaps with loads and loads more little sources, and it will now be that the phase, instead of jumping from 0 to phi to 2 phi, is just varying continuously, and this is the important point, and linearly as I go across the slit. Yeah, if I fill in all these gaps here, say between detectors sources 3 and 2, with lots of other little sources here in between, well, clearly the phase difference, as I keep drawing from each infinitesimal source, is just a linear delay at this point at infinity. So now, instead of having to add up this type of thing, in other words, instead of adding a lot of discrete phases, I now integrate over the phase where phi is a linear function of y, the distance going across the slit. So this is the crucial point of doing this. Once you've got your head around this part of it, the actual rest of the maths is quite easy, is that now instead of summing up lots of discrete sources, I have to integrate a lot of continuous sources across the width of the slit. So the maths is now, if you see what you're doing, the maths is not that difficult. So, and indeed, we're precisely going to use what we did for n-source interference. So we can calculate the amplitude in the far field. We're going to do now purely far field for the rest of this lecture. this plane wave approximation from our results for n-source interference. Last week we effectively did 2 sources, then 5, then many, and I derived this function for n-source interference in the lecture on Friday. Well, basically we can use exactly that approach in the far field by considering the slit. It's a funny, as I say, this is conceptually quite a challenging step. But you consider the slit as an infinite number of sources of infinitesimal separation. But specifically doing that infinitesimal separation, if you like, in a very particular way, where we just keep filling in the gaps between all of the sources. So we now have, and this is using the geometry of figure 71, yeah, where the y-axis is going along the slit, the x. So if you like, if there's a great big, plane wave behind the blackboard and it comes through a narrow slit, this is the x direction. This is the wave going in this direction. This is the y direction. This is the direction across, and so, as I say, like if the slit's got a certain width, then suddenly there's some kind of brightness in the middle, and then it drops to 0. So the y direction is in this way. So we now have that phi. In fact, I'll make this really explicit. We now, so, excuse me, I'm going to slightly rewrite this. So instead of the phase difference phi between discrete sources, so what we were doing last week was adding up. We were saying, well, I've got 2 sources which are a difference. There's my k, here's my distance. So last time, when we were doing the discrete problem, again, I think I've brought my notes for this. I hope so. Again, I emailed this out to everyone. This one wasn't filmed. This was from the problem class last week. Well, clearly, the phase difference between 2 adjacent oscillators was 2 pi d over lambda sine theta, whereas now, instead of having this d, the distance between adjacent oscillators, I've just got something which is just a linear function of phi here. So this is where it links to last week. That was what we were looking at in discrete n-source interference. The phase difference is now given by, we've got, let's emphasize it, the linear continuous function So it's a linear continuous function, but extremely straightforward. Phi as a function of y is just 2 pi over lambda y sine theta. So this, let's make this equation 16.2. Yeah. So in this case, when we calculate slit diffraction, the phase delay, and again, it's pretty obvious when you think about it. If again, I'm like looking for a diffracted ray somewhere over by the fire exit in the geometry that I mentioned, well, a plane wave arrives and it's slightly further from this side of the slit. So here's the plane wave's arrived. It's hit my slit, yeah, and the wave from this side has got to go slightly further from the wave from this side, but the delay is just going to be exactly linear as I go across this slit at this distant point. So the phase is just varying linearly as I go across the slit. And again, because we went to the trouble of solving that 5-source pattern, comparing with the 5-source interference problem, which we did explicitly, the 5-source interference problem, and that again, that was the problem class was week 6, wasn't it, last week? Problem class in week 6. Well, instead of the summation, which in that was very easy, it was e to the 2I phi plus e to the I phi plus 1 plus e to the minus I phi plus e to the minus 2I phi. So again, I just put that back up for a minute here, that we saw precisely that for those 5 sources with the, of course, now this phase was fixed for each source. They were 5 fixed points. Instead of doing that, instead of having a sum over phases, we now have an integral over the continuous function given in equation 16.2. So instead of that, which was a sum of discrete sources, we have to calculate the integral from w halves to minus w halves as the lower limit, e to the I phi dy. So if you like, you can think of this as a lot of infinitesimal strips of width dy. Each of them acts as a source of scattering, but then instead of adding over all these strips, of course, because they're infinitesimal, we integrate with respect to y to get the total scattering from the detector. And then we substitute in, for our phase factor, we have to evaluate the integral from minus w halves to plus w halves, sorry, that's a half there, of e to the 2 pi I y sine theta over lambda, all integrated with respect to y. It's a major equation. Let's make that 1613. So mathematically, if I want to calculate the amplitude, remember we're calculating the amplitude. We still haven't done the step of getting from the amplitude to the intensity. We're just calculating the amplitude as a function of phase angle. And of course, for any fixed wavelength of radiation, say for example a red laser, 650 nanometers, and at any given fixed angle, we can abbreviate sine theta over lambda to be u. That's a perfect, we can always go forwards and backwards. There's a one-to-one mapping here between u and the angle, because basically we've got a fixed monochromatic incident radiation, lambda's just a number, and of course it is for small angles. I'll come back to why it's only relevant for small angles. U and sine theta just map to each other. So using u is equal to sine theta over lambda, just a trivial change of variable, which I will label equation 16.4. So that's one part, and noting that we can extend the limits to plus or minus infinity. And again, this is an important step. There's 2 steps going on here. First is a trivial one. I'm just saying, well, I'm going to label sine theta over lambda as u. And I can always, as I say, for monochromatic radiation, then I calculate at a certain angle, then there's a fixed u value. I calculate at another angle, there's a fixed u value, and another angle, there's a fixed u value. So I've just changed variable in a very straightforward way. But also, there's nothing, our imaginary plane wave behind the blackboard, there's nothing coming through here, yeah? there's absolutely nothing coming through because the blackboard is opaque. Actually, the whole thing's opaque, but with your imagination, you can imagine that this little bit in the middle here is transparent. And so if I extend the limit of the integral to minus infinity on this side, I'm just adding in a load of zeros. Yeah, I'm just adding a load of zeros. I now have this bit here where I do the integral, but likewise, there's some light coming through here. This part is genuinely illuminated. There are photons arriving here which are coming through. But if I add in up to plus infinity on this side, well, there's nothing coming through there anyway. So I can certainly add a lot of zeros to my integral without changing its result. So I can change the limits. And again, let's be explicit about this, because there is no contribution to the integral outside the range. The slit is, in other words, the illumination only goes from minus W halves to plus W halves. So if I extend the integration limits to infinity, this integral, referring of course to the integral above, equation 16.3, is of the form integral from minus infinity to plus infinity of e to the 2 pi I y u dy, i.e. a Fourier transform. I cannot possibly emphasize strongly enough the importance of this result. We've only kind of demonstrated it for slit diffraction, but it's true. Not going to prove it in general. If you want to look in a book like Hecht and get a rigorous proof that this is true in general, of course you can. I've demonstrated that just by the analogy between many source interference and considering a slit to be effectively a lot of very infinitesimally spaced sources all next to one another, that if I put it, remember this only applies to the detector at infinity. This is emphatically not true for the near field, which is not given by the Fourier transform. The far field diffraction pattern is calculated by taking the Fourier transform of the aperture function. And this result is general and reduces the whole of far field diffraction optics to Fourier transforms that you've been doing with Phil. And you've already done the Fourier transform of the top hat function, so I'm not going to waste too much time ploughing through the maths. So the amplitude across the slit is a top hat function. Obviously gets its name from its shape. And you'll have seen this before. And indeed, Phil is also going to do the double top hat function for you to do Young's double slit interference. And I'll come back to that a little bit on Friday afternoon. But first, as I say, we're going to do the single slit. You see, it's arbitrary what the height of the function is. It's just we know that it's uniform illumination. But what isn't arbitrary is that it's 0 until minus W halves, and then it's got some width. So you've done all the maths recently. Its Fourier transform is well known. You don't have to revisit this. Phil will have done this with you from first principles. And if you don't know how to Fourier transform a top hat function, go back and really make sure you do, because it's the basis, if you like, of optics, certainly Fraunhofer optics. So you know that the answer is sinc psi, and that sinc psi is an abbreviation for the sine of psi over psi. So we know that the far field diffraction pattern, the amplitude of what we observe is simply the sinc of the phase angle. The phase angle, of course, we can relate to the physical angle in space very straightforwardly, exactly as we did for interference, where now psi is equal to pi w sine theta over lambda. So let's make this equation 16.6. Obviously we want to be able to relate this function in terms of phase angle to our real system. W is the width of the slit, theta is the angle where we're measuring the amplitude, or rather the intensity of the radiation, and lambda is the fixed wavelength. So we've got a completely clean analytic solution, and psi is the phase difference at the edge of the slit. Let's be careful here. As compared to the middle of the slit. Remember, we've done the integral in the way, if I define the phase in the as 0 in the middle of the slit, again, you see all that I'm doing there is, if you just go back a second to this equation, I should probably have gone with the boards the other way, I'll get there eventually. Here, 2y sine theta over lambda, well obviously the limit of the integral, remember we took the limit to be y here w halves, yeah? So the outer limit of the integral, my y just becomes w halves, yeah? And of course the 2's cancelled and I'm left with pi w sine theta over lambda. So it's the phase at the edge of the slit as compared with the middle of the slit. That is the physical meaning of the phase angle, and because this is the general function for the phase angle, well it's obviously true at the edge where y is equal to w halves, and that gives us this limit of the integral. So coming back to the results, our intensity comes out very naturally in terms of the phase angle, and then we convert it to the physical problem of a slit of, and of course what the phase angle will be will depend on how wide the slit is, where our detector, what angle our detector is, and what the wavelength of the incident radiation is. But in general we'll always end up with this sinc function. So to remind you, the function sinc phi, I mean the reason it's got its own abbreviation is because it comes up in physics so much. It comes up in diffraction so much. Rather than saying sine psi over psi, it's such a common function in diffraction, we give it its own name. This is why it's got its own name. This function gives us the amplitude. Yeah, we've just added the waves up. So the intensity, so sinc squared phi, the square of this function, gives us the intensity of single slit diffraction. So we've done the job now. We've calculated exactly the intensity of single slit diffraction. So we take a Fourier transform of the aperture function. The aperture function's a top hat. That gives us the sinc function, which we can always relate to our physical variables, and then we square it to get the amplitude. And this is illustrated in figure 64 of the course handout. Just move this out of the way. So, figure 64 of the course handout, I hope you will find vaguely familiar from last Friday. I hope I find it at all, actually, but when I do find it, you find it familiar. Yes, it is not an accident. Of course, it's the same as n-source interference, because that was plotted, remember, by taking n to be enormously large. And so we, of course, have to reinterpret slightly now. This was for n enormously large, the intensity. We'll just call this the sink. And, of course, it is normalised to 1. Again, you all know sine psi is equal to psi minus psi cubed over 3 factorial plus psi to the 5th over 5 factorial. So if I divide by psi, divided by psi gives me 1 minus psi squared over 3 factorial, etc. So the limit as psi goes to 0, although both the numerator and denominator are going to 0, is quite clearly by making the Maclaurin expansion of the sign is clearly equal to 1. So 1 there. And now I've plotted it as a function. Again, let's reinterpret. We haven't got n discrete oscillators next to each other with a discrete phase angle psi. We've just got this continuous angle psi here. And this is what the function looks like. And you can calculate the intensity exactly. Obviously, all you do is you square the sinc function and you've got the complete intensity pattern. There's one thing that, again, that is different, and be careful with this analogy of n-source interference with the single slit. We completely lose the big other maxima. Yeah? Remember, the big other maxima were at d sine theta is m lambda. Yeah, this happened to be the 6 oscillator problem. Well, they all add up in the middle, they always do, but we lose this because remember, sine theta is m lambda over d. We're now taking these sources, their individual separation is going to 0. Remember, we've got a lot of infinitesimally spaced sources, so it doesn't matter at any finite wavelength. If this is going to 0, then this is greater than 1, and it's got no solution for higher angles. So the single slit diffraction, you just get the straight through beam, but you do get these little lumps of scattering around it. But you don't get like coming through a narrow slit. It will go straight down the middle and all add up, and then just at these low angles we'll get subsidiary bumps, but then there's nothing out there. Yeah, it's just a straight through. And, you know, we'd be very surprised, actually, if you shine a torch at a laser at a slit, you'd be really surprised if with a single slit, you know, the beam split up into wide angles. I mean, physics might be like that, but it isn't. So this is what happens. So it's very similar to the n-source. At low angles, it's basically identical. If you plot this function with n very large, you get the identical function as the sinc, but then again, it just dies away with these little bumps and then there's nothing further out. So there is an important difference to the n-source interference because there's no way with d tending to 0 that we can get things to add up. So just make some comments on this function. The side lobes occur at psi is 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. Yeah, that's just labelling up the sinc. I mean, you know, the sinc function you can pop in your calculator, plot it out, and of course, you know, this is precisely what you get. And just to emphasise, again, I've scribbled it on that view graph. Be careful that pi halves is not one of these cases. Yeah, pi halves is within the central lump of the sinc function. You know, it's easy to think, oh, there's my sine function. So my sine is doing this, and obviously it's 0 here. My sinc function is so this is, if you like, my pi and my 2 pi. Yeah. So, but you've got to be very careful because at this end, your denominator is also going to 0. So the limit of the sinc function is 1. It's not like a sine near the origin. So it doesn't matter how it's going, it's somehow going to reach 1. Yeah. So the pi halves bit is not a side lobe. It's within the central maximum in Fraunhofer diffraction is much broader than the other lumps, yeah? Much broader. And then at 3 halves, this function reaches -1. Well, we'll come to exactly the correct intensity in a minute. The sine function reaches -1, and so you get the square of the sine function is as big as you can get, in other words, equal to 1. Now, strictly speaking, you should differentiate the sinc function to find all the maxima, all the maxima, yeah, the lobes of the function. You should differentiate that function, but basically, the easier method is to note, well, sine squared can't be greater than 1. Yeah? So the maxima of the function, I've got to be pretty close to where sine squared psi is equal to 1. It can't get any bigger than that. You know, the sine, if you take the sine squared, is obviously just going to go and so on. And so the sine squared function can't get bigger than 1. So you can say, well, you're going to get the maxima. Being careful that pi halves is not a solution to this, you know, then you really do have to consider the sinc function. But once you've got away from the central maximum, well, obviously, you know, the sine function gets its biggest values then, because we're not considering pi halves because of this different behaviour of the sinc, but afterwards 3 pi halves, 5 pi halves, and so on. We'll just go on. So you don't even need to do calculus. You can say, provided you're careful with the psi half case, which is not a maximum of sinc squared psi, all the remaining maxima are just simply obtainable in this straightforward way. So the side lobes are going to occur at these values of, and here I've remember plotted sine psi. So this bit will be all part of the central maximum. Your first side lobe, well, it's easy to get the intensity because you've got, well, I mean, the whole point of choosing that as the first side lobe was that the sine is equal to 1. So the denominator, sine squared, is 1, and the numerator, by definition, is psi squared, is just 3 pi squared. So the intensity, compared with the intensity at psi 0, it's normalised the whole function so that the intensity is 1 when psi is equal to 0. Well, I've just got 4 over 9 pi squared. In other words, about 4.5% of the intensity. At the next side lobe, it's 1 over 5 pi squared, about 1.6 of the percent of the intensity, and so on and so on. And you can see that even by the time I've got out to the third lobe at 7 pi halves, the intensity is less than 1% of the straight through beam, of the beam at the origin. So it's quite a rapidly varying function, and you don't need to consider it, you know, to be, you very rarely would consider it further out. So I'd just like to finish with a note on that. So at 3 high, at psi is 3 pi halves. Just move this up a bit, get this one out of the way. The intensity of the first peak, I1, is equal to the intensity at the centre, that stands for psi is 0, times 1, that's my sine squared, over 3 pi halves squared, that's my sine squared, that's my psi squared, which is obviously just equal to 4I0 over 9 pi squared, which is equal to 0.045 I0, etc. You can work all the other ones out very straightforwardly for yourself. However, very much the most important point that I want to leave you with, I mean, we've done now single slit diffraction completely rigorously by taking the Fourier transform of the aperture function, and we can do absolutely any far field diffraction problem now just by looking up a book of Fourier transforms, basically. We've done the principles, and this is the message to carry away from this lecture is definitely the last line. The result that the amplitude of the diffracted wave is given by, once we have got the amplitude, of course we can get the intensity from squaring, is given by the Fourier transform of the aperture function and of course we've only done the case, if you like, of a 1D aperture function. We've only done a 1D Fourier transform. Phi was a function of the single variable y. We were assuming, if you like, the slit was infinitely long but had a finite width, and we were just looking at the way the wave spread out from that. Is general, brackets for far field diffraction. Just to emphasise again that we've still got the thornier problem of near field diffraction to come, and we'll treat that less rigorously because it's quite mathematically complex. So Wednesday we'll be looking at Fourier transforms of more useful functions like circles, and usually telescopes and microscopes have circular rather than slit-like apertures. So we'll do that next time.